In this video, I want to talk about sampling distributions, and it's really just some kind of overall ideas about samples and estimating populations that then will help us when we finish our review by talking about confidence intervals and hypothesis testing. So, a couple reminders: a parameter and versus a statistic. I hope you remember a parameter comes from a population, and a statistic comes from a sample. And we try to use statistics to estimate parameters. We try to gather a sample mean in order to get an idea about a population mean, or we try and gather a sample proportion in order to estimate a population proportion, and so on. So we try to gather stats to estimate parameters. Now, bias and variability. Bias, if I could kind of do this in a picture, let me start with bias. Let me put this picture right here. If I have a kind of a number line and I say my population mean is mu, and then I go out and I collect a bunch of sample means to estimate it. If my distribution is centered like this and my x bars are centered up here, we call this a biased distribution because the sample mean is not a good estimate of the population mean. In fact, looking at this, we would be pretty confident that in fact our mean is probably up here. We'd be wrong. This is a biased estimator. So variability, let me put that picture kind of right over here. In this case, let's say we have a mean. Variability simply means that it's very spread out. Okay, that it does something like this. That we do, kind of believe that at the center of our distribution is the population mean or population proportion, the parameter, but we've got a lot of spread that allows for a lot of variability in here. Okay, so bias means it doesn't estimate, variability means a lot of spread. Now the central limit theorem. The central limit theorem says that if a sample size is large enough, I'm going to write n is, I'm going to put kind of some quotes there, large. What we can say is that we probably have a shape that's approximately normal, a sampling distribution, okay, that's centered around the actual parameter, okay. That's if the sample size is large enough. We think our sampling distribution will actually be an unbiased good estimator. So, to think about it this way, you say it's actually centered the way it's supposed to be, like that, okay. That our x bar is where it's supposed to be. Now, what do I mean by sample size? Well, this really depends on the kind of thing you're collecting. If it's a sample mean, if that's what you're collecting, then remember that means that the sample size should be bigger than 30, greater than or equal to. If it's a proportion, a p hat that you've been taking, then that's that np and minus n times 1 minus p is greater than 10. If you're doing like chi-square, like you're doing those kinds of things, then remember it's that expected counts are bigger than 5. Okay? So, what we hope, and let me just kind of go back here to talk about this kind of overall idea. We want a sample distribution, right, to be unbiased, meaning centered on the correct thing. We want to have it's going to have variability. Not every single time we take a sample are we going to land right on the population, the parameter. But we want to be close, and we want to end up there most of the time, with maybe some smaller probability type things off on the ends. How we know that's going to happen, or how we think that's going to happen, if the sample is large enough, and large is in quotes because it depends on the kind of problem, If the sample is large enough, we think that our sample distribution will appear approximately normal, centered on the parameter. Now, how do we know it's large enough? If we're talking sample means, it's that magic 30 number. If we're talking sample proportions, it's that NP and N times 1 minus P bigger than 10. Okay? Now, we have lots of different variabilities. I'm going to drag those in a second. So what we think in a sampling distribution, just to recap that, we should be centered on the parameter, whatever it may be. Sample means, sample proportions, should be getting closer and closer to the parameter. The shape, again, that should be normal as long as that kind of sample size condition has been met. And the variability, this is describing standard error. And if you remember, that's very dependent on what kind of problem we're talking about. Okay, so here are those standard errors. So the sample means, if you've collected X bars, this is the variability. If you've collected sample proportions, here's your variability. Difference in sample means. Difference in proportions. Okay, so those are all on the formula sheet. Okay, that's how your sample distribution is laid out. So kind of the big ideas here, okay, is that a statistic estimates a parameter. That statistic, to be unbiased, should be centered on the parameter. Now, we don't think that every single time it'll be exactly correct, so that's why we allow some variability calculated using these formulas. If the sample size is large enough, we think that distribution will be approximately normal with that parameter at its center. What do we mean by large enough? It's these conditions we've talked about when we did confidence intervals and hypothesis testing. How can we get less variability? Well, you'll notice each one of these formulas has an N in the denominator. Larger sample sizes will decrease variability. Now, bias, we hope that by collecting good, simple, random samples, we have unbiased results. We're not ensured of that. And in fact, if we have a biased set of data and we just keep adding more to it, there might be a reason for the bias. It might be a question that people are embarrassed to answer. So just saying, well, I asked 100 people about smoking or something like that. Now I've asked 500 and it's still biased. Well, maybe if the reason it's biased is that people don't want to answer truthfully for whatever reason, just adding more doesn't necessarily fix the bias, but it will decrease variability. Okay, so this has been one big talk about sampling distributions, and then in the next video we're going to start talking about how we use this to do confidence intervals.